All right, so we're almost at that goal line, and we got. I'm gonna make two more videos. We're not gonna get as far as I'd like to, but we're gonna cover chapters 6.1 and 6.2. So you just hang in there because we're almost done. And again, I appreciate all of your work. Okay, so really quickly, you recall that unlike many of my colleagues, the way I teach linear algebra is I begin the section with a week and a half studying vectors, the types of vectors that you would have used in, say, a physics class. And what I want to do now is I want to revisit some of those ideas. But here's the more important thing. Like, if I were to ask you basic geometric concepts like distance or length or, say, perpendicularity in, say, 2 dimensions, R2, well, that's easy to intuit and it's easy to, visualize. But what about if you want to study those geometric concepts in other dimensions, right? Like, what if I were to ask you to explain to me perpendicularity in R20, right? Do you understand that at some point we need to have some more formal definitions because our intuitions are not going to be there. So let's go ahead and begin. So we're going to start with just the dot product, and we're going to revisit, and then we're going to make sure we understand the basics and then start to add, okay? So just imagine I have two vectors, right? Vector V, vector W. And in this particular case, I actually know my ij notation for both of these vectors. Well, what we saw was that the definition of the dot product, the dot products that we used, would simply take those the a sub 1, basically your whatever is attached to the I notation, multiplied by a sub 2, and plus b sub 1 multiplied by b sub 2. And what was quite intriguing, quite fascinating, was the fact that this was, in this regard, if you took for example, if you took a scalar times a vector, you still had a vector, but in this case, a vector times a vector was actually a scalar. Now, both of this definition here assumes that we actually know the coordinates of the points that we want to take the dot product of. But let's go ahead and discuss. Well, what if we actually don't know the coordinates of V or the coordinates of W? What if instead we know, let's say, the angle between the two vectors, and then we know the lengths of our vectors? Well, I understand that we can move from length of vector to coordinate. We can just place the initial point at 0 and make things nice and neat, nice and easy. But my question still stands. What if you take away your coordinate system and you just are, let's say, in some space, and what you know, let's go ahead and so you can take a look at the picture at the bottom. What you know is the length of V, right? So we know the length of V, and we know the length of W, and we also know theta, the angle between V and W. Well, what if you took the product of all three of those, right? So if you had the magnitude of V times the magnitude of W times, well, we can't just multiply a magnitude times a magnitude multiplied by an angle, right? Because what we'll do is we'll write times cosine of that angle theta. Now, why cosine? So first off, let me answer this question. What if you took the product of all three of those? What would you have? Well, you would also have the definition of a dot product. Okay, that's also the dot V dot W. So we have two ways of computing a dot product of V and W, but one with an angle and one without an angle. Now, here in a second, I'm going to ask you how would you actually solve for the angle. But before I go any farther, I want to make sure that you understand something really quickly, and that is, why do we choose cosine? Right? I mean, maybe you thought about that before. If you've seen this definition of the dot product, why cosine? Why not sine or some other trigonometric function? And the reason is we want our two vectors to be in the same direction when we multiply their lengths. Right? That's the idea. That's the reason why we choose cosine of theta. While we're here, while I have this picture in front of you, let's towards the end of this section, we're going to discuss things like projections, right? So projections, and if you'd like, I can see if I can make this intuitive as well. So imagine that you have some type of flashlight, or let's say a sun, shining its beautiful rays down upon vector v. Right? Now, let's imagine the shadow that would be cast. And this, so you can imagine the shadow being when vector v is what we say projected onto vector w. Okay, you don't have to write this down because we'll come back to it, right? So this would be vector v being projected onto vector w. And we'll come back to some of these ideas in just a second, and then I could continue with revisiting some of these concepts that we've already discussed, but I'm not going to insult you. I'm going to assume that you remember things like dot products, and I want to add some additional insight. So again, a dot product, another word for a dot product is what we call an inner product. And let's get into our matrix notation. How do we think about dot products when we don't have our ij notation? What if we actually have our vector? We still have a vector, but our vector is now nestled within some type of matrices. Well, so look, if you have two vectors, u and v, now I don't know what dimension we are in, but it doesn't matter. If we are in some dimension, Rn, right? We could be in R2 or R3, etc. But what we can say is, if vector u and vector v are in Rn, then the vector v and vector u can be represented by some n by 1 matrix, right? So that's kind of what you're seeing here, some n by 1 matrix. And now the question, and we'll come back to what I have written above. Question, for example, 1, they're asking you to compute a dot product, right? They want you to compute u dot v, and they want you to compute v dot u. Well, I agree with you that if you're savvy enough, you could go from this matrix notation back to your ijk notation and then compute your dot products. But how do we, since we're here, what if it's a much larger n by 1 matrix? How do we compute a dot product, or even think about a dot product in this matrix form? Well, okay. So back up here. So if u is some n by 1 matrix, right? Some vector. If vector u is an n by 1 matrix, then recall the idea of a transpose, right? So vector transpose. So u transpose. If you recall, the transpose is when the columns become the rows and the rows become the columns. So if we have n columns by 1 row, or I should say n rows by 1 column, the transpose of that would be what? Be 1 row by n columns, right? And that's exactly what you're seeing here with u and u transpose. And the idea of a dot product in this matrix form is as follows. So we're going to go ahead and answer example 1. We're given U, we're given the definition of U, we're given the definition of V. So when we are asked to compute U dot V, the way we should think about that is being asked to compute U transpose dot V. Okay, so that is going to allow us to actually do this. Does it make sense to you that structurally speaking, and I'll just look, this is a 3 by 1 and this is a 3 by 1. So structurally, you cannot multiply them, right? Because what I'm highlighting here have to match in order to multiply our two matrices. So they don't match. But as soon as you transpose one of them, then your structure will match up. So let's go ahead and write U transpose. So we don't have to think about it very much. Just remember that U only has one column. So that one column becomes the one row. So 2, -5, -1. Now, we didn't do anything to V, so we're still going to leave that as 3, 2, -3. Now we have what? We have a 3, or I should say a 1 by 3 and a 3 by 1. And then a 3 by 1. So now we actually can compute. Now I'm not gonna do V dot U for you. I'm just gonna do one of these. These are fairly easy concepts. So we have a 1 row by 3 columns, and to that we want to multiply 3 rows by 1 column. Okay, so now structurally we definitely can multiply them. And what should the result be? Well, if you recall, I made mention that the result, what I'm highlighting in yellow here, is a 1 by 1 matrix. And what is a 1 by 1 matrix? Well, 1 by 1 matrix is just a scalar. Hold on for a second. So the dot product of two matrices is a 1 by 1 matrix. The dot products in IJ notation is a scalar, but a 1 by 1 matrix is a scalar. So do you see how we still maintain our understanding of dot products? Let's just go ahead and finish this up. So we can use our, we would go, columns by rows. So we would end up with 2 times 3 plus -5 times 2 plus -1 times -3. And the result of all that little bit of arithmetic is -1. So you could think about that as -1 if you wanted to keep your matrix notation, but again, since a 1 by 1 matrix is just a scalar, this is our solution. Now you could try V dot U, and what would you expect to find? Well, you should expect to also get -1. Same idea. And you just like if you saw that when you did vector V times vector W, that dot W, that would be the same as W dot V. Okay. So we have a better understanding of dot product when our vectors are not, say, now does it make sense to the class, right? Whoever is watching this video, that I could make this vector as large as I'd like, 50 times 1. Either way, we now know how to find dot products. Okay, so now let's discuss length. right? Because the length of between 2 points, or how do we discuss the length of a vector? All right, so I'm going to break this definition down for you a little bit. So the length, or what we call the norm, of some vector v, well, you would think of length as being a positive scalar, and that makes sense. So it is a non-negative scalar defined by the following. Well, notice this series of equal symbols here. So let's just make sure we understand. So if we start with vector v being defined in our ij notation, so that makes sense. I mean, then whatever a is, the absolute value of a would be the distance from 0 to this point here, and this would be the absolute value of b. And obviously vector v would be thought of as the hypotenuse of some right triangle. Now, okay, well, it's very easy to understand right triangle trigonometry. We can just make use of Pythagorean's theorem. So if v is equal to, if v can be thought of as a hypotenuse, then, okay, well then what does that mean? That means that v squared, obviously, is equal to a squared plus b squared, or, taking the square root of both sides, v can be thought of as the square root of a squared plus b squared, okay? All right, so again, revisiting old concepts, but what's another way of thinking about v squared? What's another way of thinking about v squared? So, well, v squared is just the idea of vector v multiplied by itself, right? V squared, so that's the dot product, v dot v. Well, we have another way of writing v squared. So the way we should think about this is that if you have v dot v, and since v dot v is equal to v squared, then that would mean the dot product of v with itself is also equal to a squared plus b squared, right? Makes perfect sense. So now you're at least starting to see the relationship of how we can say the length or the magnitude of some vector v is equal to the square root of vector v dot itself, which is equal to the square root of, well, in this case, they used v sub 1, v sub 2, and you can, instead of, say, the a's and the b's, but you kind of get the gist. You kind of get the gist. And it also makes sense as to why we can say, well, the magnitude squared, right, which is what we're saying here, is equal to the dot product. So again, old ideas, just trying to shed some light on them. Okay, so let's think really quickly about the unit vector. Remember, we know that the unit vector is some vector with a length of 1. What we often ask is find a unit vector in the same direction as some other vector, right? And you recall that the definition of that was given as follows. So this is simple. You're simply dividing a non-zero vector v by its own length. That's why if I divide 3 by the length of 3, then of course we're getting 1, right? We're dividing, so we're just simply taking a vector. We are maintaining its direction. The direction doesn't change, but we're just rewriting it with a length of 1. Okay. So example 2, they give us some vector, right? And if you were to think about this, example 2, if you were to think about it in n by 1 notation, this would be 1, negative 2, 2, 0. So the question could be written this way as well. But nevertheless, here is v, how we've defined v. And what we're asked is to find a unit vector, which we'll call u, that's in the same direction as v. All right. Well, how do we proceed? Well, we want to write u equals, and let's go ahead and revisit the definition, right? Well, we would need vector v, which we have. That's no problem. And we would need the magnitude of v squared. All right, well, let's start with the magnitude of v squared. So this is why I started off by making the statement that the magnitude of vector v squared can be written as the dot product of v with itself. So that can help us, because this is not in ij, k, whatever would come after that notation. So we would want to go ahead and compute the dot product, v dot itself. Okay, so we can go ahead and write this. It would be 1 times 1 plus negative 2 times negative 2. Right, I could write these all as squared. It would be just a lot easier, but just so we maintain our same notation. Then it would be 2 times 2, and finally it would be plus 0 times 0. All of that gets us to 9. Okay. So, in other words, we can make the statement that, what? Well, the magnitude, my apologies, I wrote a squared here because I was thinking squared. In case you want to know what just happened, I had a squared here because I was thinking about here, but this is the notation. There's no square. So at this stage, we've taken our dot product, and we have the following. The magnitude of v squared, which we interpreted as the dot product of v with itself, is equal to 9. But what we want for our unit vector in the same direction formula is we want just the magnitude of v. Well, that would be equal to what? The square root of 9. Right? You can get rid of the square by taking the square root, which is just equal to 3. All right, now I know what to do. So this is the definition. I don't like to think about it as a fraction. I would rather think about it as 1 over the magnitude of v multiplied by v. That's a much, in my opinion, that's a much better way of thinking about it. So let's go ahead and put everything where we need it to be. So 1 over magnitude of v, that would be 1/3. And we're distributing that to what? Well, we're distributing that, I won't use my parentheses. We're distributing that to the following vector. 1, negative 2, 2, 0. If you ever wonder why a lot of the textbooks tend to write their vectors like this, as opposed to, say, like this, it's more of a way to save space in the textbook itself. So, okay, so what is the result? Well, here it is. Here's the answer. That's just 1/3, and then negative 2/3. So 1/3, negative 2/3, positive 2/3, and we still got 0. All right. So this new vector should be in the same direction as vector v, but it should have a length of 1. And of course, you could always go back and compute its length to make sure its length is equal to 1. Okay, you would just take the dot product of this new vector. If you take the dot product of this new vector with itself, you should get 1. All right, so example 3. So now we'll start to use some new language from, or some language from a post-midterm with some language prior to midterm. So it says let W, so let W be some subspace of R2. Okay, so we'll take this piece by piece. So I went ahead and copied some R2 YX coordinate system here so we can visualize this. But this is, remember, W is a subspace of R2. So W should exist somewhere in here, right? Somewhere in R2. Now, the next part says that W is spanned by the following vector. Okay, so it's spanned by the following vector. So let's actually interpret that. Let's make sure we understand that. So spanned by this point. Okay, so what does that mean? What does that even mean here? Well, it's not that bad to interpret. Let's go ahead. Maybe it's better if we write x as an n by 1 vector, one that we're used to. So this would be 2/3, 1. And what they're saying when they say that W is spanned by this vector, that would mean the following. That would mean that let's just attach some scalar, c, to x. Now, what I've done here is I've taken the liberty of drawing x for us. So this is vector x. And now think about, well, what would it mean to attach a scalar to that? Well, that would mean you could have 2x or 3x or 4x or 0x or negative 2x. Does it make sense to you that that would just be a line moving through R2 through vector x? That would be the span. That would be the geometric interpretation of the subspace W. Now, what are we asked? What is asked of us? Well, we want to find a unit vector. Now we're going to call that z this time instead of u. We're going to find a unit vector that is a basis for W. Oh, okay, wait a minute. So a unit vector that is a basis for W. Okay. So let's proceed. So z equals, that's what we want. Well, so clearly we need to maintain the direction, right? And but we want its length to be 1. So in other words, whatever z is, we know it's going to be a unit vector. So that's when it's going to be, so back to some vector, let's say x divided by the magnitude of x, right? Which I normally write as 1 over the magnitude of x times x. All right. Now I will show you something that most textbooks do, and this is optional here. So will you agree with me that I can choose any c, any scalar that I want, and I would be within the subspace W, correct? So I'm just gonna parrot what your textbook does. Your textbook is gonna just assume that c, we're gonna just assume that c is equal to something like, say, 3. so that we can rewrite this vector x without a fraction. So imagine me putting a 3 in here attached to vector x. Well, what would that be? Well, that would be 2, 3. Right? 3 times 2/3 is 2, and 3 times 1 is 3. Now, I cannot call that x anymore because we've already defined x to be 2/3 1. So I have to call this new vector 2, 3 something else. We'll just call it y. All right? So let me get back to I want a unit vector. We'll call it called z. That is the basis for w. So let's start with maintaining its direction and having a unit vector. I had x here just a second ago, but again, since I'm parroting what your textbook's doing, let's rewrite this with the y. So this would be what? This would be 1 over the magnitude of y multiplied by y. All right, well, let's go ahead and do this. Let's go ahead and start with what is the magnitude of y. Well, the magnitude of y is going to be equal to, recall, the square root of 2 squared plus 3 squared. So therefore, the magnitude of y is equal to the square root of 13. Okay, so now I know what to put here for magnitude of y. So z is equal to 1 over the square root of 13. And now that's going to be multiplied by y, which is 2, 3. All right, well, what do we get? We get a vector. And that vector would be 2 square roots of 13, 3 square roots of 13. All right, well, what can we be sure of? We can be sure that this is a unit vector, as long as we did all of our arithmetic correctly. So it has a length of 1, so that meets this criteria. And we can be sure that it serves as a basis for w, because I can still, this is very easy to form a basis of a line, is I still can get, so imagine if I were to try to plot the point z. So that would be way down in here, right? Let's just say it's way, well, yeah, so probably 2 divided by the square root of 13, yes, so it's way down in here. But even from here, I can still scale that and get to back to x. I can get back to any other vector that I'd like. So nevertheless, this is both a basis and a unit vector, and we are done with example 3. All right, so now we want to discuss distance. All right, distance. Well, maybe it's worth starting in R1, right? So if you have, let's say, a point A and a point B, it's very easy to interpret what is the distance between A and B, right? And the distance between A and B can simply be thought of as 8 minus 2, right? And we use absolute values, because we could think of it as 2 minus 8, the absolute value of 2 minus 8, or we could think of it as the absolute value of 8 minus 2. Either way, we use that absolute value to make sure that we get the same distance, right? Because the difference between 2 and 8 and 2, as long as you have absolute values, is the same. Forgive me. So now we want to discuss distance, not in R1, not in R2, but in Rn. All right, how do we interpret distance in Rn? Okay. Well, first off, let me go ahead and show you the notation that we're going to be using. So the notation for distance between two vectors so the distance is distance, well, I made that plural, distance between two vectors, we'll say u and v, the way that we would write that is the following. Okay? So that's pretty easy to remember, but that's what we mean to say the distance between two vectors. And the good news is we don't have to have a distance formula or any, even though we could definitely go back and revisit the distance formula and show how intuitively it makes sense in higher dimensions as well. But it's really just a matter of saying what is the magnitude of u minus v, right? So, and again, that's going to be an absolute value and a positive number. So let's look at the geometry here. So remember, here's v, here's u. You have these guys, right? So you would know v and u, but you're asking, what is the distance between v and u? Well, the distance between v and u, as we saw, it can be defined as the magnitude of u minus v. All right. So let's go ahead and put this definition to work for us. Let's go ahead and compute the distance between u and v given the following. So u is at 7,1 and v is at 3,2. So I will spare me drawing that out for you. As long as you can understand figure 4 above. But how do we do this? Well, to proceed, because we want the distance u between u and v. Well, let's finish this up. So first thing I'm going to need is u minus v, right? So let's go ahead and do that. So u minus v, that would be u is 7,1, v is 3,2. So u minus v, 7 minus 3 is 4, 1 minus 2 is -1. So this right here, this is the vector u minus v. All right. Now what I want is the magnitude of that vector. So the magnitude of u minus v, well, it's just as easy to use our square root of, well, let's go ahead and take 4 squared plus -1 squared, which is the square root of 17. That is the distance. Okay, don't know what units we're in, but that is the distance. Okay, so now let's discuss perpendicularity, right? To say that two vectors are orthogonal, right? The words orthogonal, the words normal, the words perpendicular, they're basically we're going to use them as synonyms, and the only reason we have these 3 different vocabulary words to represent the same concept is because when you're discussing vectors, when you're talking about perpendicularity, when discussing vectors, we use the word orthogonal. We use the word perpendicular when we're discussing lines, and so forth. So for our purposes, these are just synonyms. Okay, and let me go ahead and start read theorem 2. So two vectors u and v are orthogonal if and only if. Well, what does this mean here? Well, that is just the Pythagorean theorem, right? But let's discuss it this way. So u is orthogonal to v if and only if the length from u to v is equal to the length of u to -v. Now let me see if I can make sense of why this is something you want to grab hold of, right? Again, if you're going to stay in R2, it's very easy to think about vectors being perpendicular. But if you're in R50, how are you going to start to think about orthogonal vectors, perpendicularity? How are you going to consider these in higher dimensions? Well, that's what we need. So take, for example, this little drawing that I have here. So here's some vector u, here's v. So if this is v, then this would be negative v. Make sense? Now, what I'm trying to say here, that u is orthogonal to v if and only if the length from u to v, well, what is the length from u to v? Let's start there. So the length from u to v, that is this right here, is equal to the length from u to negative v. Okay. So the length, the length would be the magnitude of what? Well, in this case, it would be u minus v. And this would be the magnitude of u minus what? Minus negative v. Right, so this is a much better way of thinking about perpendicularity, is if the length from u to v is equal to the length from u to negative v. All right, now all I'm doing, this or statement is just saying this is two different ways. That would also mean that the distance of u to v squared would also have to equal the distance from u to v squared, right? Because if u to v has to equal to u to negative v, then distance u to v squared has to equal the distance from u to v squared. Basically, I wrote this as, this should be u to negative v, actually. Write that. Okay. Let me write u to negative v. Okay, so what I've done, and this is just using some basic theorems that we've discussed on the previous page. We use theorem 1b, theorem 1a multiple times. But in other words, I can rewrite, if you'll just allow me, I can rewrite the distance from u to v squared, and let me make sure I'm writing each one of these correctly, because I threw a negative in there. And I want to make sure. Nope, I did. Now, no, so this is u to v. This one should be u to negative v. Okay. So if you allow me, just using some of those properties from that theorem 1, I can rewrite distance from u to negative v as follows. And I can rewrite distance squared, I should say. And I can write the distance from u to v squared as follows. So you can try it on your own. It's pretty simple. You're just doing some dot products and you're distributing, all of that nature. But I can get us to where we want to be without all of that little baby algebra, baby arithmetic. If you allow me, that saying distance from u to v squared, distance from u to negative v squared can be rewritten this way. Will you allow me that statement? Well, you have no choice in this matter, because you can't even convey your opinion to me while since we're over the internet. So what if I take what I've boxed in here? Let's subtract magnitude of u squared, subtract magnitude of v squared. Don't you see that these would cancel out? Right? Doesn't that make sense that those would be canceled out? So what we would be left with at that point is just 2, and I'll get rid of the lines over the v, 2 u v would equal negative 2 u v. And of course, these are dots, right? These are dot products. Now let me pose the question to you. When would this be true? When would this be true? When would this be a true statement? Well, there's only but one scenario. Well, there's two scenarios where this would be true. Let's start with the trivial case of when this would be true. If u and v are the zero vector, then of course this is true, right? if let's just say u is 0, then 2 times 0 times v would equal negative 2 times 0 times v, right? So that's the trivial case. So that's one that's one scenario. When else would this be true? This is the more important question. This is to see who's actually been paying attention. When also would this be true? Well, this would also be true. So one, if u or v is the 0 vector, right? That's somewhat trivial. The more important one is if u dot v equals 0. And now tell me, do you recall when the dot products of two vectors is 0, what does that actually mean? Well, that would mean that they are perpendicular, right? And that's exactly what we're saying here. That's what we said at the beginning of the semester, first week. We were talking about dot products. When the dot product is 0, you have orthogonal vectors. And now we're making a statement. Look, two vectors are orthogonal if and only if u plus v, the magnitude of u plus v squared is equal to magnitude of u squared plus magnitude of v squared. And we're going through all of this. So either one of these would justify these statements. One of the interesting consequences of this is from this statement is we have to accept something, even if it doesn't quite intuitively make any sense. This means that the 0 vector, I'll write it this way. So the 0 vector is perpendicular to every vector in Rn. It's orthogonal to every vector in Rn. Now, I understand that you may just be of the type that just accepts whatever your math teachers tell you, but I can recall sitting in class thinking, well, wait a minute, how the heck, right, here's the 0 vector, how the heck can this 0 vector be perpendicular to anything? Well, it's an interesting idea. How about for now that we just say it's a consequence of some definitions? How's that? All right. So we have to accept this consequence. Ready? Let's go ahead and start to wrap this up. We're almost done with 6.1. All right, so the definition here states it all. Two vectors u and v in any Rn, right, 50-dimensional space. We say vectors u and v in Rn are orthogonal to each other if u dot v is equal to 0. All right, if the dot product of u and v is 0, your vectors are still orthogonal, even if you're in higher dimensional space. All right, last bit of material, and we're going to talk about this a little bit more in the next section, but the idea of, let me give you a definition, right? So what I'm underlining right now is the definition of what we call an orthogonal complement of W. Okay, so what do we mean by orthogonal complement of W? Well, it's defined as the set of all vectors that are orthogonal to some subspace W, right? So hold on. So W is a subspace of some larger vector space. And I'm saying, look, if somebody talks to you about the orthogonal complement of W, well, really what they're talking about when they say that is there's some set of vectors, right? So the set of all vectors that are orthogonal to the same subspace W. So every single vector that's orthogonal to W makes up the orthogonal complement of W. And the way you denote orthogonal complement is what I'm circling right here. That's W with a little perpendicular sign. Okay, you can read through example 6 if you'd like on your own time. This, you can kind of see the geometry of this statement here. So notice that's more important to me, to my learning. So let's think of W. Here's this W, here's this subspace, right? And notice this line running through the zero vector in W would be perpendicular to subspace W. And now you can think of it as, you can read through example 6, which also answers itself. But anyway, we're done with 6.1. We will, when I come back, we'll do the very last section. We would have gone a little bit farther had this been without all the interruptions, a lecture class, but we're going to do one more section, which is 6.2, and then we are done with this class. See you there.